Yeah, there are some elements here. So we'll talk about that. So this is on transfer functions and input-output differential equations. Essentially, I'm going to define a transfer function in the first little bit here, and then I'm going to talk about how to derive it from an input-output differential equation. And it's really it's something that we talked about in the fall for those of you in mechatronics. There are going to be some elements over the next few weeks that are going to be reviewed for folks who are in mechatronics, but not all of the elements. So don't let that lull you into a false sense of security. We don't want you to feel secure. Insecurity is where I want you to be. Okay, a healthy amount that allows you to still function, but doesn't let you get comfortable. Okay.
You ensure that every time you sign up.
Yeah. Okay, so much of it appears in volume 1, but not all of it. So the Laplace Transform, which we denote with the script L, is cool. And I just kind of assume that you guys know how to use the Laplace Transform because you took differential equations, and that is one topic that is solidly part of differential equations class, is Laplace Transforms. It is used to solve differential equations and define the transfer function h, another awesome dynamic system representation. So we have the input-output differential equation representation of a dynamic system, which, God, you know, I feel like it's overlooked a lot, so maybe I should just write this. You guys remember this? Sum of the forces on something is equal to mass times the acceleration. You guys remember that?
Only on weekdays.
Yeah. Newton had something to say about this, and this is a differential equation.
Yes, it is.
I don't know if you guys, I know that some of you recognize that, and I'm really glad. Others of you were never told that as you were using this. So it's a differential equation. You can get a differential equation from lots of different places. So this is probably the most universal way of writing down a dynamic model, is by writing down a scalar differential equation that describes it. So like F equals ma. The elemental equations for capacitors or inductors also give you differential equations. Everything gives you differential equations. So, sorry? So the differential equation representation is very universal, so we've been using that. State space model is another really important one, right? And deriving those we spend a lot of time in mechatronics doing, and then we're going to do some of that next week in this class too. So finding the state space model given some dynamic system is another aspect of this course, and so that's another representation of a dynamic system, okay? And the transfer function is another one, okay? And so there are ways to convert among these different representations, and there are advantages in different situations of being in different representations. So we want to be comfortable constructing dynamic system models in multiple ways, and then also in transforming that representation. Not all representations are equivalent. We talked a little bit last semester about how state space model does not, or if you convert that to a transfer function or an input-output differential equation, and you go back, it's not necessarily going to be the same. You've lost something. It's a different representation. So they're not all equivalent and identical, but they all are useful at different times. And you can convert among them. There are ways to do all of that. So we're going to learn the definition of the transfer function again, and then we're going to use it. We're going to actually not use it, but learn how to derive it from an input-output differential equation, which is our most common representation of a dynamic system. Okay? So, so the Laplace transform we're going to use, it was mostly used in your differential equations class to solve a differential equation, right? They were like, oh, look, you can solve differential equations using algebraic manipulation as long as you know how to do a transform and an inverse transform. you can do it all algebraically, which was pretty sweet. We're going to kind of use some of that, but we're not going to use it specifically to solve a differential equation all that often in this class. I mean, we can. It's just not as important to us as representing the system as a transfer function, which is our real goal here. So let's define the transfer function first. Let a system have an input u and output y. Okay? Let the Laplace transform of each be denoted u and y, both functions of complex Laplace transform variable s. A transfer function h is defined as the ratio of the Laplace transform of the output over the input. So just like that, where we have written in our usual fashion that the Laplace we could write Laplace transform of y of t is equal to y of s. So we use this notation a lot, and similarly Laplace transform of u of t is equal to u of s. We typically will take the time domain function and represent its Laplace transform as the capitalized version of it, this function of s. And often we'll also drop the of s because it becomes a little bit cumbersome, but context should help you understand what object is being referred to. The transfer function is exceedingly useful in many types of analysis. One of its most powerful aspects is that it gives us access to thinking about systems as operating on an input u and yielding an output y. So you think of the system as being represented by a transfer function h, and you have some input going in, and you have some output coming out. So this is kind of the beginning of our thinking in terms of a system. Inputs come in, outputs come out, and we kind of represent it graphically like this. The transfer function is the object that takes us from the input to the output. So, transfer functions and input-output differential equations. Consider a dynamic system described by the IO differential equation with variable y representing the output, dependent variable time t, variable u representing the input, constant coefficients a, b, order n, and having m less than or equal to n, for n being a positive integer. We have this expression, which we've seen a lot, right? Which is to say, an nth order scalar differential equation, right? With output y, input u. So this is the object we've been seeing a lot of, and I know when it's all written out in this general form, it's a little scary looking, but it's just, you know, in the first order case, it's just tau y dot plus 1 equals b1u dot plus b0u. That's for a first order. That's for n equals 1. For n equals 2, we talked about the second order quite a bit, but we can go up to nth order. We want to talk about things in general when we can, because we can get comfortable with first and second order systems all day, and then if we encounter a third order or fourth order system, then we're screwed. So we might as well talk about them all at once and then talk about special cases when we desire to, which is what we started off the semester with. We started off with talking about first and second order systems specifically. But we're going to be talking in general in this lecture. So the Laplace transform L of equation 3.2 yields something interesting. So if we take the Laplace transform of an equation, that means we have to take the Laplace transform of the left-hand side and Laplace transform of the right-hand side, okay? And I actually wrote this out because I felt like it was a little hard to parse anyway, so we would just march through the steps. So this first step, we take the Laplace transform of both sides, right? Each side of the equation is on a different line here, right, as it equals is here. So Laplace transform of the output side equals Laplace transform of the input side. Now, one of the properties of the Laplace transform, does anybody remember the Laplace transform? It has an integral definition, right? It's an integral. So the properties of an integral are going to apply for the Laplace transform. One of the properties of an integral, which also is a property of the Laplace transform, is that it distributes across summation, right? So if you have the Laplace transform of a sum, it's the same thing as taking the sum of the Laplace transforms of each element. So that's what we do here. We distribute it, and we take it one step further. We say, oh, constants can be pulled outside of the Laplace transform, right? Just like a constant can be pulled outside of an integral. So we do that. So this is our second step here. So this is how it was written at first. We then distribute and pull out the constants. So what are we left with here? We're left with a Laplace transform of a bunch of time derivatives of y on the left-hand side, and a Laplace transform of a bunch of derivatives of u, time derivatives of u on the right-hand side. All right? So reaching back to our differential equations, memory of Laplace transforms, do y'all remember that d, so if you had dy dt, which is one of our terms right here, right, dy dt, take the Laplace transform of that. Do you remember what that is? It's s times the Laplace transform of y, which is equal to s times y of s, right? And we did also, there's an initial condition in there too, but in this derivation, we're assuming zero initial conditions. This is important. So if we're assuming zero initial conditions, we're thinking about the forced response, right? Specifically the forced response. That's what the transfer function is all about. It's all about how the force contributes to the output. So it's the forced response. We're losing the information about the initial condition in this step here where we ignore those initial conditions. We don't have to do that. We could keep those initial condition terms in there and derive a general solution for y, but that's not our goal here. Our goal is to define the transfer function. So if we had a second time derivative of y with respect to t, then we would get an s squared. A third time derivative, we would get an s cubed, etc., right? So extrapolating that to n derivatives of y and m derivatives of u, we have the left-hand side turn into s to the n y plus, its coefficient is still there, an minus 1, s to the n minus 1, y plus all the way down to a0 y. And on the right-hand side, similarly, we have s's now instead of derivatives. And now we're writing things in terms of the Laplace transform of y and the Laplace transform of u. Right? So we've switched from lowercase to uppercase, which denotes that we've turned from time representations of u and y to Laplace domain representations, Laplace transform representations. So now all we need to do is solve this last expression here for y. And conveniently, y shows up in every term on the left-hand side, and we can just factor it out. It doesn't show up anywhere else. So we just factor it out, and we just divide over what is left over when we factor. So we get y equals this large fraction. So bm minus 1, or bm, I should say, s to the m plus bm minus 1, s to the m minus 1. We're going to factor u out also, we're going to put u out here. So, because it shows up in every term. We don't want to write it over and over again. So we'll factor it out. Plus down to b1 s to the 1 plus b0 divided by s to the n plus a n minus 1 s to the n minus 1 plus down to should have a plus there a1 s plus a0. So we've solved for y algebraically now, which is sweet. So if we just took the inverse Laplace transform of y, then we get y of t, which is our time response, but remember we ignored the initial conditions, so this is actually just the forced response. So it's the forced response of the system to the input u. Okay? And this is probably what you guys did. This is what you guys did in differential equations, probably for first and second order systems, and you use tables to look up what the Laplace transforms were, maybe some definitions, that kind of thing. Which is all great, and I think that in the homework there's a little bit of that to sort of refresh your memory on it. So this is all sort of like familiar stuff, but we're sort of recasting it in a representation that is thinking specifically about systems that are represented dynamically, inputs, outputs, and as the output being the forced response. Okay. However, this is not our primary concern. Rather, we are interested to solve the transfer function, or solve for the transfer function h as the ratio of the output transform y to the input transform u. In other words, we want to know what y over u is, which was our definition of the transfer function, right? Was y over u. So we're saying that this is our solution for the transfer function from the input-output differential equation. So we've found it. Okay. Exactly the reverse procedure then can be used to convert a given transfer function to an input-output differential equation. So if you're given this, you could go back to the differential equation in a very analogous way, essentially just retrace your steps. Now, do you need to go through this derivation every time? No, I would encourage you not to do that. Doing it once would be a good idea. I think it would be good for you, but doing it more than once is not necessary. Because we can essentially, by inspection of the differential equation, write down the transfer function. And we can, from inspection of the transfer function, write down the input-output differential equation. So that's what I think you guys should work toward, is being able to look at the differential equation and say, oh, wherever I see an nth time derivative of y, I'm going to have s to the n times Laplace transform of y. And thinking about solving for y over u, output over the input, and you should be good to go. So we'll do an example. The circuit shown has input-output differential equation given. So I give it to you. What is the transfer function from VL to VS? Look at how small the solution box is. We're not going to do any work besides just write down the answer. It's ridiculous. Now, I will say this. If you're on an exam and you're not feeling confident, write down a step in between. Because it's hard for me to give you credit for understanding the concept if you write down the wrong answer and there's nothing describing how you got to that answer. So you know, maybe write like an intermediate step in there, like showing u factored out, showing y factored out, and dividing over, in case you write down something wrong, and then I have like some idea of where you got that, or that you understood it at least. But the idea here is that h of s, so our output is what? Which variable in this differential equation is our output? VL. Right? VL is our output. Because we have VL as being our differentiated variable on the left-hand side. I mean, the fact that it's on the left-hand side isn't really the reason why that it's the output, but VS, the other variable in this, is the source, the input from outside, and VL is a variable in the system that's affected by VS. So it's reasonable to believe that VL would be our output variable, considering the fact that there is only one other variable in the equation. So, and also I asked for the transfer function from, actually, you know, I feel like I should switch these. This is a mix-up here. I would simply ask for the transfer function from VS as the input to VL as the output. So those should be switched. So that means our VL, so we should capitalize VL of S is our convention. And then sources are already capitalized, so there's just no good way to go besides just writing VS of S. This is the transfer function for this input-output differential equation. Now, we could go through the whole derivation that we just did for this case, but we are lazy / intelligent or something. I don't know what we are. We're something. I had my first calculus professor tell me that mathematicians are just lazy. That's why they learned math. Yeah.
So you said the input in this example was VS.
The input is VS.
So shouldn't that be on top?
So it's output over input. So for the transfer function, the definition is output over input. So y over u. So we could have I can say here output. Probably good to denote that output. Input. Output over input. So our output over our input is going to be, so you always get the numerator coefficients from your right-hand side. So our numerator coefficients, we're only going to have one, and that's so L times S to the what? 2. S squared times, it would be times VS, right? But VS we've divided over, so we don't need to write VS there. If we did write VS there, we would be incorrect. So we do not. I don't like the look of that S. That's a better S. Okay, so LS squared in the numerator, the denominator coefficients come from the left-hand side. So we get L times what? S squared plus, what's the next term? RS plus, what's the final term? 1 over C. Is there any S on this one? No. This is kind of too easy, isn't it? Yeah.
So in the derivation one, you have just like in the standard form, so your first term is going to have a coefficient. Does that matter?
So you're right. You picked up on the fact that I left the coefficient here, and I didn't put it into the standard form where I would typically divide everything by L. It's fine. If we wanted to write our transfer function in what's called standard form, we would need to divide the numerator and denominator by L to make this coefficient 1. it's not a big deal one way or the other. If it's asked for in standard form, then you should. So if you were to do that, it just gets a little messier, but the numerator actually gets a little nicer, right? The L goes away. So you get s squared divided by s squared plus it's r over L times s plus 1 over LC, which is also totally fine. So either one, this would be standard form, so probably slightly preferred.
It looks like a 3. 3 squared.
This one?
Yeah.
Oh. I don't know what's up with my S's today. My S's are all whack. Let's try that again. S squared. My 5s look like that. So
That's a B with the Johnny Bravo haircut.
oh man. I watched that once. Okay. So let's wrap that up. Do you guys have anything? Should I diss Johnny Bravo again?
Maybe the next lecture.
Mm-hmm. We'll hold off. One per lecture.